So in this week we are going to do some Scala programming. We're going to take the first steps into this new programming language and into functional programming in general. A lot of the material in this session will look very easy to you because it's familiar. But there are also some things that are fundamental, in particular the formal model of evaluation that we call the substitution model, which will be very important for the sessions later on. So it's good to pay a little attention. Okay, let's get into it. Every non-trivial language provides primitive expressions that represents the simplest elements of the language, and then some ways to combine expressions and ways to abstract expressions. Abstraction means that we introduce a name for an expression, and then further on we can reference the expression by its name. One way to approach functional programming is to see it a little bit like a calculator. In fact, most functional languages have an interactive shell, that's also sometimes called a REPL, which stands for read, eval, print loop. And in that shell you can type expressions and it will respond with the results of evaluating these expressions. In Scala you can start the REPL simply by typing Scala. So if you write Scala here, then you get the REPL. That assumes that you have a standard Scala distribution. That's actually not a requirement for this course. For the course we asked you to install SBT, the Scala build tool, instead. From the SBT you can also get a REPL simply by typing SBT console. It's the same REPL, so it doesn't matter whether you start that with Scala and SBT console. Once you are in the REPL you can type expressions like 43. You can also define values, such as radius equals 10, and the REPL would in each case respond if you have an expression with the expression's type, in this case that is int, and the expression's value. If you have a definition like radius, it would just give you the type of the definition. You can also define floating point numbers, and afterwards you can refer to what you have defined before. Now let's have a look at evaluation. We have seen how that these expressions were evaluated. How exactly did that happen? Well, the rules are well known from simple algebra. To evaluate a non-primitive expression, we typically take the leftmost operator, subject to the rules of precedence. We evaluate the operands of that operator, typically left before right, and we apply the operator to the operands. What about evaluating a name? Well, that's evaluated by replacing it with the right-hand side of its definition. We apply these steps one by one until finally the evaluation process results in a value. And for the moment a value is just a number. Later on we'll also consider other kinds of values. So let's see an example. Here's the evaluation of the arithmetic expression 2 times pi times radius. What's happening there? First thing we do is we look up the name pi and we get its definition 3.14159. Then we perform the arithmetic operation on the left. Then we look up the radius, evaluate radius yielding 10, and finally we perform the final multiplication yielding the result. Definitions can also have parameters. For instance, we can define a square function by writing def square. Then comes the parameter x of type double, and then comes the right-hand side x times x. The right-hand side refers to the parameter x. And the evaluation then would yield the expected. Square of 2 would give 4, square of 5 plus 4 would give 81. We can of course also have parameterized definitions that refer to parameterized functions, as in the sum of squares function here, that takes 2 parameters, x and y of type double, and it computes the square x and square y and sums them. You've seen in the last slide that function parameters come with their type, and this type is given after the parameter name and a colon in Scala. So you would write x colon double y colon int. You can also give the return type of a function that follows after the parameter list. The primitive types are written as in Java, but they are capitalized. So int, for example, is a 32-bit integer, double is a 64-bit floating point number, and Boolean represents the Boolean type with values true and false. Now, how are function applications evaluated? In fact, they are evaluated in a way that's very similar to operators. We first evaluate all function arguments going from left to right. We then replace the function application by the function's right-hand side. And at the same time, we replace the formal parameters of the function by the actual arguments. Let's see how this works in an example. We start with sum of squares of 3 and 2 plus 2. The 2 plus 2 gets rewritten to a value 4, and we have sum of squares 3, 4. Then we take the definition of sum of squares, that was square of x plus square of y, and we replace the application by this right-hand side, where at the same time we replace the parameters x and y by the actual arguments 3 and 4. We then repeat the process with the square application. Square of 3 becomes 3 times 3, the right-hand side of square, where 3 replaces the parameter x. We get an arithmetic simplification, and we do the same thing for the right-hand operators, yielding the final value 25. This scheme of expression evaluation is called the substitution model. The idea underlying this model is that all evaluation does is reduce an expression to a value. And that reduction can be expressed by a sequence of simple rewriting steps that rewrite the expression term itself until it is a value, very similar to what you would do in algebraic simplification. Simple as it is, this model is very powerful. In fact, it has been shown that it can express every algorithm, so it's equivalent to what you would call a Turing machine. This has been shown a long time before functional programming, in fact a long time before computers, by a logician called Alonzo Church in the lambda calculus. He did that in the 30s of the last century. You might have come across lambda calculus in theoretical computer science, and if you did, then you know how to make the connection to this model. If you didn't, don't worry, we won't need the theory for following the course. What's important though is to know that lambda calculus as a model and the substitution model can be applied only to expressions that do not have a side effect. Now, what is a side effect? A typical side effect would be an expression called C++, where C is a variable, and evaluating this expression means that you return the old value of C and at the same time you increment the value. So at the next time you return the value, you would return a value 1 larger than before. Turns out there's no good way to represent this evaluation sequence by a simple rewriting of this term. You need something else, like a store, where the current value of the variable is kept. In other words, the expression C++ has a side effect on the current value of the variable, and that side effect cannot be expressed by the substitution model. So one of the motivations for ruling out side effects in functional programming is that we can keep to the simple model of evaluation. Once we have the substitution model, another question comes up. Does every expression reduce to a value in a finite number of steps? In fact, the answer is no. Here's a counterexample. Let's write a simple function def loop int equals loop. And let's then refer to the name loop. What would happen? Well, according to our model, we have to evaluate that name, which happens by replacing the name by its right-hand side. The right-hand side is loop again. So we have reduced the name to itself, and this can go on ad infinitum. Another way to visualize this reduction sequence is by starting with loop and then reducing to the same term again. We've seen that the Scala interpreter reduces function arguments to values before rewriting the function application. That's not the only possible reduction strategy. Alternatively, one could apply the function to unreduced arguments. For instance, we could start with sum of squares 3, 2 plus 2, and then go on as follows. We keep the right-hand side, we don't reduce it to 4, and we simply pass it as an expression to the square function. We then simplify the right-hand side as before, and then do the same thing again, pass the expression 2 plus 2 to this occurrence of square that gives 2 plus 2 twice in the multiplication. We then simplify it in 2 further steps to arrive at the final result, 25. Now you've seen 2 ways to evaluate the same expression. The first evaluation strategy is known as call by value. The second is known as call by name. An important theorem, in fact of lambda calculus, is that both strategies reduce to the same final value as long as the reduced expression consists of pure functions and both evaluations terminate. Call by value has the advantage that every function argument is evaluated only once. Call by name has the advantage that a function argument is not evaluated at all if the corresponding parameter is not used in the evaluation of the function's body. Here's a question. Say you're given the following function definition. Def test of x and y equals x times x. For each of the following function applications, indicate which evaluation strategy is fastest, by which we mean has the fewest reduction steps. There's first test of 2, 3, then test of 3 plus 4, 8, test 7, 2 times 4, and finally test 3 plus 4, 2 times 4. Let's see how we would answer this question. I have the test function here, and I have the calls that I want to compare here. Let's start with the first one, test 2, 3. How would that evaluate? Well, test 2, 3, we take the definition of test, x times x. So that would give 2 times 2, and that would reduce to 4. And in fact, it would reduce to 4 under both evaluation strategies, both call by name and call by value, because we have started with already evaluated arguments, so there is no choice in the matter. So here the answer would be they have the same complexity. Let's do the next one. Test 3 plus 4, 8. Under call by value, we have to evaluate the arguments. So we get test 7, 8. And that gives us 7 times 7 and the final result. Whereas under call by name, we get 3 plus 4 times 3 plus 4. That reduces to 7 times 3 plus 4, 7 times 7, and 49, in one step more than the call by value version. So call by value has the advantage here. Let's look at the third example, test of 7 and 2 times 4. Here with call by value we would get a test of 7 and 8. Finally 7 times 7 and the final. Whereas with call by name we would get 7 times 7, 49. So in this case we have avoided the unnecessary computation of the second argument, and call by name is faster. The fourth example, test 3 plus 4, 2 times 4, combines the evaluations of the second and third example, so it comes as no surprise that it's again a draw, that call by value and call by name reduce in the same number of steps then.